This is section 3.7, Implicit Differentiation, page 1. All right, so we're going to start off with this equation, x squared plus y squared equals 16, and we want to find dy dx. Well, in order to find dy dx, we have to have an equation that's y equals blah, blah, blah with x's. So let's go ahead and take this equation and let's solve for y. So y squared is equal to 16 minus x squared. Then take the square root, and we remember that when you take the square root of both sides of an equation, we get plus or minus. Now what happened on this one though now is when we solve for y, we have two separate equations. So let's call one of them y sub 1, and that's the positive square root of 16 minus x squared. And let's call y sub 2 to be the negative square root of 16 minus x squared. All right, now let's go ahead and find the derivative of each one. So let's find y1. I'm going to rewrite that so we don't see the square root. We see it as a half exponent. And then find the derivative of this. Now, since I asked you to find dy dx instead of y prime, different notation for the same thing, let's keep that notation. So dy sub 1 over dx is, and we have a chain rule going on here, so outside most function, 1/2, leave the inside alone, to the negative 1/2, times the derivative of the inside, negative 2x. When we go through to simplify this, clean this up a bit, we see this 2 and this negative 2 divide out, and we are left with then negative x over, and let's take this square root, or this half exponent, which is negative, and move it back to the bottom, and we'll flip it back to the square root of 16 minus x squared. All right, one step further. Do you recognize this 16 minus x squared, this square root of 16 minus x squared? Yeah, that was exactly y sub 1. So dy sub 1 dx is negative x over y sub 1. Looking at y sub 2 over here, again we'll do the same thing, rewrite that, and we'll do a derivative, and this derivative is dy sub 2 dx, and we'll have negative 1/2 times the 16 minus x squared to the negative 1/2 times the derivative of the inside, which is a negative 2x. Cleaning this up, again the 2's will divide out, and this time we have a negative 1 times a negative x, that's just x, over, and we can put this back in the denominator as a square root, 16 minus x squared. All right, now look at this. This 16 minus x squared, square root, that's negative y sub 2. So dy sub 2 over dx is x over negative y sub 2. All right, did it matter that I separated these into y sub 1 and y sub 2? So if you cover up the sub 1 part, then the derivative over here is just negative x over y. And over here, if you cover up the sub 2 part, then the derivative is still opposite of x over y. What this tells us is that it didn't matter if we separated these functions or not, that the derivative dy dx is just opposite x over y. All right, now that was one way to do this problem. this is an okay method. There is a better method. All right, let's look at that one. And for this one, we're going to start with the very same equation, x squared plus y squared equals 16. And instead of solving for y, we are just going to say, okay, I know I can solve for y here. So we're basically going to assume that y is equal to some function of x. We could solve for y, and it is some function of x. So what we can do then is rewrite this y squared as some function of x squared, because y is some f of x, so I've replaced out that y with f of x. Now we can do a derivative, and you've done things like this before. The derivative of this x squared is 2x plus, now this notation you should recognize, that's a chain rule. So when we do the derivative here, this outsidemost function is the squared, so we do that. 2, leave the inside alone to the first, times, now the derivative of the inside, f prime of x, equals, and on the right side, the derivative of 16 is 0. Okay, now let's think about what we're trying to do here. We've just done the derivative. What were we trying to do? Ultimately, we're trying to find dy dx. I've changed the notation here with this f of x idea. So what we really need to do is we need to solve for f prime. That's the dy dx that we're looking for. So to do this, let's go ahead and take this 2x here, and we'll subtract the 2x over to the other side. So we have 2 times f of x times f prime of x equals negative 2x. Then again, we're solving for f prime, so let's divide by 2f of x. And we will have f prime of x is negative 2x divided by 2 f of x. 2's divide out. And we have f prime of x equals, well, the numerator is x, denominator is f of x, but what did we say way back in the beginning? What was f of x? Yeah, it was y. So we can change that f of x back into y, and there's our derivative. Ooh, I lost my negative sign. Negative x over y. Oh, look at that. That matches what we did earlier. A little bit nicer to write out than to have to do two separate equations. All right, now we had an okay method, a better method. Guess what? There is a best method. And this best method, what we do is, again, we start off just like we did before, x squared plus y squared equals 16. But instead of substituting out this f of x over here for the y, we just kind of tuck that away and say, all right, I know that y is some f of x. And we just start to do a derivative right here, and that's 2x plus, now that y squared is just this, it's f of x squared. So we do the derivative of the outside, which is the square, so that's 2y. That's like this, 2f of x, times now the derivative of the inside, and this y is the inside function, just like f of x was the inside function over here. And the derivative of that y is dy dx. And on the right side, the derivative of 16, still 0. Solving for dy dx, let's subtract that 2x. 2y times dy dx is negative 2x. Divide out the 2y. And the 2's divide out. And we have dy dx equals opposite of x over y. Isn't that pretty? Okay, again, sometimes this is difficult for people to see, and what you're kind of imagining here is that this y is some function of x. You're just not actually writing it. You're just thinking, okay, it is so messy that I can't even write it. I am just going to leave it as some hidden function of x inside of here. And then I do the derivative. Outside most is 2. So 2y to the first, and then times the derivative of the inside, and that inside is that y, and it's so messy that you can't even write it. We just have to leave it as a y. And our derivative then is of the y is the dy dx. This concept over here is implicit differentiation. That concept is implicit differentiation. If you're a little bit iffy, that's okay. Let's take a look at some examples on the next pages.